Welcome back to Distributed and Multi-GPU Deep Learning. So we'll be continuing on the overview on the need for distributed deep learning. So we'll be continuing on the overview. So in the previous topic, we talked about the need for large-scale machine learning, and we also identified that there are two broad groups of problem. One being a CPU-bound problem where the training data could fit within the RAM of the computer, but the processing power required is more than what a single computer can do, what we call CPU bound. And another group of problems is related to the memory or memory bound problems where the training data set itself is very large, and therefore in order to actually do the machine learning training, you actually need to be able to load in the data gradually in chunks rather than all at one go with a giant pandas data frame. So in order to solve that memory bound problem, we need to have more scalable out-of-core algorithms that are able to do incremental learning and also able to dispute that load over time, right? That means that instead of trying to do the training all at one go with a very big data set, we are going to load in chunks of data and then do incremental learning. And we learn it from the data a bit or a chunk at a time. Now we're going to revisit those two problems, the CPU bound and memory bound, in the context of deep learning. Because deep learning is very complex machine learning algorithms, and they have certain requirements. And we're going to visit why we need to also consider CPU bound or memory bound problems and how we are going to solve it in the context of deep learning. So if you look at this chart as seen here, in terms of CPU bound, we can see that actually the models are growing at an exponential rate, and over the last 10 years, it is a hyper exponential rate since the scale at the side is actually a log scale, right? It is not, it's in powers of 10 rather than a linear scale. So actually, although it looks like a straight line here, it's actually an exponential curve if you use a normal linear scale. So it was already growing very quickly in terms of the petaflops or the flops, the floating point operations per second that you need over the last few decades. But since 2010, when we have very complex deep neural networks for CNN and increasingly for transformer-based for natural language processing, you can see that the growth rate has sort of shot up, right? So the curve, you can see a marked difference in the steepness of the curve. So if it was exponential previously, it has become hyper exponential over the last decade or so. DQN is a deep Q, actually a deep reinforcement learning. It's a deep Q learning network, and AlphaGo is also based on reinforcement learning. So you can see actually reinforcement learning based techniques, right, using deep learning, they do add to the complexity quite a bit. And the previous simpler CNN like LeNet, they are still growing on this normal exponential curve, but the more complex ones like VGG and ResNet, they are on this very steep path as well. The most recent ones like the transformer-based natural language processing uh, deep learning networks, they are making this curve grow even further up, right? Because those models are very, very complex compared with what was actually available in the previous generation. So yes, ResNet and VGG were the king of the hill in terms of complexity in the past, but they have been overtaken by some of the new deep reinforcement learning models as well as transformer-based models. So we can see that in terms of flops, the model complexity or model size has increased, and so we are increasingly going further and further into the realm of the CPU bound problem, right? So earlier neural networks, we could probably train it on a single machine, and even VGG and ResNet, they could be trained on a single machine, but some of the large scale neural networks, the transformer models and also the deep reinforcement models, increasingly we need to actually use more than one CPU and GPU as well. It just cannot be squeezed and trained within a reasonable amount of time with one single GPU or CPU resource. So this is actually the problem, because we can see that the trend is very clear. It is growing very rapidly in the past and even more rapidly in more recent times. Next, we're going to take a look at the trade-off between accuracy, training time, and inference time. So this particular graph shows the trade-off between accuracy on the vertical axis and training time in terms of the flops required to do the training on the horizontal axis. And we can see that there is basically more or less a relationship between the two, where increase in the number of flops also results in a larger accuracy. So you can see that ResNet down here is a low number of flops. ResNet, this is a simple ResNet, low number of flops, but also the accuracy is relatively on the low end. Whereas if you go up to more complex ResNets, the number of flops required increases, and you can find that the number of the accuracy increases as well, and all the way to the most complex neural networks, which takes a huge amount of flops to do the training, like this SENet here. The accuracy is also amongst the best that we can have. But we do notice that actually there is this particular family called the efficient net, which does very well because it gives you the maximum accuracy for a relatively modest number of gigaflops required for training. So this is actually a very efficient neural network architecture in terms of the amount of training time it needs versus the accuracy that it can achieve. But of course, there is a maximum level that it can go before it so max out, right? But certainly, it's quite impressive that this family of neural networks, they can achieve efficiency much higher than the other families of neural networks. So that's actually the trade-off in terms of the training time versus the accuracy. So more training time and more flops that you put into the problem translates to an increase in the model performance, a higher accuracy. How about the inference time? So on this graph, the vertical axis is again the accuracy, and on the horizontal axis, we actually have the run time, the time it takes to make a prediction or an inference. So as it's different from the training time, because for training time, we're talking about the total amount of computations you need in order to do the training for a particular neural network. So for this is actually for prediction, right, or inference. How many milliseconds it takes to actually run one single inference from your data. So we are not training the neural network. So it's actually pretty fast. It's in order of milliseconds. But then again, you can see that for the more complex neural networks, the inference time does increase. So the simpler ResNet, it takes like almost close to 0 milliseconds. But then as the complexity of the ResNet increases, the inference time increases as well. And the accuracy is basically limited by the training and the complexity of the neural network. So it will hit a certain maximum depending on the architecture. And our good and very efficient net, you can see that it has a very clear trend where the efficiency gets better the more complex the network is, but the runtime also increases quite a bit as compared with the other neural networks. But you get very good accuracy. And interesting thing is that the training time is very efficient, but that does not translate into efficiency in terms of the execution time, right? The inference time, because even though it achieves a very high accuracy, you see that the runtime is actually pretty large compared with something like ResNet. So it goes that efficient net is very efficient for training, but when it comes to inference, it does take up more time to do the inference, but it does achieve a very high level accuracy for this amount of inference time. What is not so good would probably be this one down here, DenseNet. It takes probably the largest amount of inference time to compute, but the accuracy is like almost half that of the efficient net. So it's not ideal, but this is just another class of neural networks architectures that are actually available. Of course, if you need to have just a quick answer, the go-to algorithms will be those down here, the MobileNet and ResNet, which have very low computational requirements, both for training as well as inference. And if you are going to actually deploy this on maybe a very CPU limited device, this would probably be the way to go in terms of deployment, right? On a mobile device, you probably go for MobileNet or ResNet. So there's some implications for this graph, even for distributed deep learning. So you can have a very large infrastructure for training, and then you can have gigaflops or petaflops of CPU resources being available in your training cluster. But ultimately, if you're going to deploy that same model in a more CPU limit or computation limited device, you have to take into consideration that you cannot have too complex a model. So if your target device is a mobile device or a more limited device, definitely you would not want to go for something like efficient net, which takes a huge amount of computational resource just to run it. So even though you may have the resource to do the training for the efficient net, you probably cannot deploy on the actual target device itself. So you have to balance the training time versus the infrastructure that you need to actually do the inference. One way to overcome this, of course, is to split the task. So you have a front end, okay, just the user interface that runs on the mobile device, and when it needs to make an inference, it makes a network call, make a web service call into the back end, and the back end then runs the network for you and does the inference. So in that way, you can have a very big server infrastructure behind your mobile application, and then you're not limited to only using the simpler models. You can even use something like efficient net. The only drawback for that arrangement would be the network latency, because it does take some time for the packets from your mobile device to travel across the network to the cloud where you have your model, and then the model serving infrastructure will then send it back to your device, and then you get the final result. So that latency of transmission and getting the result is something that you have to factor into the design. So we come to the last slide and some comments about the comparison between the GPU bound and memory bound problems and the need for distributed deep learning. So we can see that since the model size has a very clear trend of increasing in the number of gigaflops that it needs, we do need to actually move from having just one single training server to multiple training servers, because as the size of the neural network increases, it's no longer possible to train some of these gigantic deep learning networks with only one single GPU or CPU resource. So it moves from being a simple problem to a CPU bound problem or GPU bound problem. So we actually need to have a cluster of training servers now for some of the newer large deep neural networks. Now the other problem is also present for large deep neural networks, because in order to train a deep neural network of a certain complexity, you need a lot more data than you would require for normal classic machine learning algorithms. Deep learning neural networks, they are very large in their learning capacity, and they can actually, they are universal approximators. They can approximate any complex function or shape, no matter how complex it is. But in order to do that, it also needs to have a lot of training data to feed into the neural network, or else you will find that this algorithm will not be as effective as other algorithms, right? So it is proportional. So you need higher CPU resource, but at the same time, in order to feed enough data to this resource requirement, you also need a lot of data, and therefore you will also run into the memory bound problem, because the memory of one single machine is not enough to actually load all the training data or training samples at one go. You will definitely exceed the size. You're talking about deep learning networks with a billion parameters or more. It will definitely exceed the size of the training data required to basically train a billion parameters, will exceed the size of the RAM in one single machine. But the good news is that neural networks inherently support incremental learning, the incremental gradient descent that we talked about in the other topic. They are supported in the deep neural networks, and we have a big choice of different optimization algorithms as well. So making use of that property, that incremental learning, we can also tackle the memory bound problem at the same time. So the trick to getting this to work is to see how we can actually spread the load, both in terms of computation, we do distributed training, and at the same time spread the load in terms of the memory requirement. How do we split the data across multiple devices as well? So unlike the many of the problems that we encounter in large-scale machine learning, in distributed training for deep learning, we actually have to solve both these problems, both in terms of the training data size being excessively large, as well as the CPU requirements or the computational requirements. How can we actually spread this over multiple GPU enabled servers rather than trying to do the training on one single large machine? So thank you for your attention, and we've come to the end of this set of slides, and I'll see you in the next set.